Objective 8 for Calculus BC is one of our approximation methods for the year. It's called local linearization or linear approximations. What are we really doing here? We're using the tangent line. Using tangent line to approximate the function. Okay, now why are we able to use a tangent line, something that's straight, to approximate curves potentially? Well, for any curve, if we do values that are close to the point of tangency, then for values that are very, very close to the point of tangency, the tangent line can do at least a decent approximation of the actual function. So that's really what we're doing. And some books, they'll actually come up with a formula and all that kind of stuff. But really, we're just doing a tangent line approximation, which equation of a line, y minus y1 equals the slope times x minus x1, and you put it into the y equals form, so move the y sub 1 over, and to make it local linearization, you trade the y for an L of x. Literally, that's all you're doing to get the linearization or the local linear. It's the tangent line. That's really all it is. Okay, got two sample problems here for us to do. Let's go ahead and work through them. And this is the way that our textbook actually does it, but really, I mean, it's like you're just doing a tangent line to approximate, and when you're using the approximation, you're going to be doing something pretty close to the point of tangency. So here's a function, f of x is the square root of 1 plus 3x. Okay, and so the at a equals 8, or in other words, the point of tangency is going to be 8 comma something for this particular problem. So 8 comma something. We're going to need that y coordinate right there, so we might as well go ahead and plug it in. So f of 8 is root 1 plus 3 times 8, which is root 25, which is 5. Okay, so the point of tangency is going to be 8 comma 5, and we need the slope of the tangent line, okay, the derivative. So f prime of x, okay, so square root, that's really a quantity to the 1/2 power. So we have 1/2 times 1 plus 3x to the negative 1/2 times the derivative of the guts, which is 3. Okay, now this cleans up to be 3 over 2 square root 1 plus 3x. Okay, and so the slope of the tangent line at that point of tangency, f prime of 8, is 3 over 2 root. Now we already did the square, so that's square root of 25 really, because 1 plus 3 times 8, so 3/10. Okay, so I've got my point of tangency, 8 comma 5, and my slope, 3/10, and so if I write my tangent line equation, so y minus, what was it, 5? Yeah, y minus 5 equals 3/10 times x minus 8. So it's my linear approximation if I move the -5 to the other side and just replace the y with an L of x. So 3/10 times x minus 8 plus 5. There is my local linearization. So for values close to 8, this is a pretty decent approximation. Now, do not distribute the 3/10. Leave it in this form because when we do our approximations, it's a lot nicer in this form. So let me show you why. So we are trying to approximate f of 7.9. Okay, so f of 7.9 is approximately L of 7.9, and this is equal to, I'm running out of space, 3/10 times 7.9 minus 8 plus 5. Now, normally I don't normally show that step right there. Normally I go immediately, because what is 7.9 minus 8? It's -0.1, but fractions, because when we're doing this kind of stuff, a lot of times you find yourself without any technology, you're finding yourself with a calculator. So it's -1/10. And so really I would be doing 3/10 times -1/10 plus 5. Okay, so this is equal to -3/100 plus 5, which is, and that's -0.03, so 4.97. Could say 4 97/100. Okay, so f of 7.9 is approximately that. Now, so we found the local linearization. We found L of x. We used it to approximate f of 7.9. Now compare this to the actual value of 7.9. So grab your calculator right now. Okay, I'm grabbing my calculator. I forgot to grab it ahead of time, but just grab your scientific calculator. We're going to do f of 7.9. So f of 7.9 is square root 1 plus 3 times 7.9. Now, 7.9 is only 1/10 away from 8, so this should be a pretty decent approximation. So let's see, we've got so we're really doing the square root of 24.7. And so it's approximately 4.9699, and there's some more there, but so how did our approximation compare? They're pretty doggone close, aren't they? Okay, so that's really what we're doing with this problem. We're going to try one more right now. Okay, so f of x equals -1/x, and the a of -2, and we're doing f of -1.9, and so on. Basically the same process we just did on this other one. Okay, so f prime of x is negative times, okay, 1/x, and it's like we can go ahead and 1/x is x to the -1, but really, I mean, this turns out to be -1/x squared. So the derivative is positive 1/x squared. Okay, so I want the slope at the point of tangency, so I'm doing f prime of -2, which is 1/-2 squared, which is 1/4. I also need my point of tangency, the whole point, so -2 comma, okay, f of -2 is -1 over -2, which is positive 1/2. Okay, and so if I combine those, and you know, it's like once you've done them a little bit, I mean, you could go straight to the L of x. L of x is equal to, I've got my slope, times x minus a -2 and plus 1/2. Okay, so there's my linearization, local linearization. Okay, so I want to use that to approximate f of -1.9. So f of -1.9 is approximately L of -1.9, which is 1/4 times, okay, now -1.9 plus 2, isn't that 1/10? Plus 1/2, okay, which is 1/40th plus 1/2, getting them the same language. So this is 21/40ths. Okay, without a calculator, that's what you want. Okay, that's our approximation. Now we're going to be comparing it to the other. So go ahead and grab your calculator. Let's do 21 divided by 40. And that is equal to 0.525. And we're going to compare that to the actual f of -1.9 is equal to opposite of 1 over -1.9, so we can see it's positive. 1 divided by 1.9 is approximately 5.263, and we can see our approximation is pretty good approximation. So the tangent line is a pretty good approximator as long as you are close to the point of tangency. So, you know, I mean, the further you get away from the point of tangency, it's potentially not so good. But as long as you're close, it will be a pretty good way to approximate the original function.